Gravity. It's the force that keeps us anchored to the ground, guides the planets in their orbits, and shapes the very fabric of our universe. But what if everything we thought we knew about gravity was wrong? What if gravity doesn't exist as we understand it? In this video, we will explore the fascinating history of gravity, the revolutionary theories that challenge its existence, and ultimately debunk the claim that gravity isn't real. Stay tuned as we journey through centuries of scientific thought and cutting-edge research to uncover the truth about one of the most fundamental forces in the cosmos. Gravity has intrigued humanity since ancient times. Early philosophers like Aristotle believed that objects fall toward the Earth due to their inherent nature. He posited that heavier objects fall faster than lighter ones, a notion later debunked by Galileo Galilei. In Aristotle's worldview, the Earth was the center of the universe and everything moved towards it. This geocentric view was accepted for centuries until the scientific revolution. However, Aristotle's ideas laid the groundwork for future inquiry into the nature of motion and forces. In the 17th century, Sir Isaac Newton formulated the law of universal gravitation, describing gravity as a force that attracts two bodies towards each other. Newton's law mathematically defined gravity, providing a framework that explained planetary orbits and the motion of objects on Earth. Newton's seminal work, Philosophiae Naturalis Principia Mathematica, published in 1687, outlined his three laws of motion and the law of universal gravitation. He proposed that every mass exerts an attractive force on every other mass, which decreases with the square of the distance between them. This inverse square law allowed for precise calculations of planetary movements and laid the foundation for classical mechanics. Albert Einstein revolutionized our understanding of gravity with his theory of general relativity in the early 20th century. Einstein proposed that gravity is not a force but a curvature of spacetime caused by mass. This theory has been confirmed by numerous experiments and observations, such as the bending of light around massive objects and the precise calculations of Mercury's orbit. Einstein's equations of general relativity describe how matter and energy influence the curvature of spacetime. This curvature dictates the motion of objects, explaining why planets orbit stars and why light bends around massive objects like black holes. General relativity has withstood rigorous testing, including observations of gravitational waves and the precession of Mercury's orbit. Despite the robustness of these theories, there are still hypotheses that challenge our conventional understanding of gravity. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in the 1980s, suggests modifications to Newton's laws to account for the observed behaviors of galaxies without invoking dark matter. MOND posits that at very low accelerations, the gravitational attraction between objects becomes stronger than predicted by Newtonian physics. MOND alters the gravitational force equation at low accelerations, providing a better fit for the rotation curves of galaxies. This theory challenges the necessity of dark matter but does not negate the existence of gravity. Milgram's modifications introduce a new constant which implies that the gravitational force deviates from the inverse square law. While MOND successfully explains certain galactic phenomena, it lacks the broad applicability and predictive power of general relativity. Quantum mechanics, which governs the behavior of particles at microscopic scales, struggles to incorporate gravity. The quest for a theory of quantum gravity has led to various hypotheses, such as string theory and loop quantum gravity. String theory posits that fundamental particles are not point-like but rather one-dimensional strings whose vibrations determine particle properties. Loop quantum gravity, on the other hand, suggests that spacetime itself has a discrete structure at the smallest scales. Both theories aim to reconcile gravity with quantum mechanics, but have yet to be experimentally verified. String theory proposes multiple dimensions beyond the familiar 3 spatial and 1 temporal dimension, potentially offering a unified framework for all fundamental forces. Loop quantum gravity, however, focuses on quantizing spacetime itself, predicting a granular structure that could resolve singularities like those found in black holes. Erik Verlinde proposed the idea of emergent gravity, suggesting that gravity is not a fundamental force, but an emergent phenomenon, resulting from the thermodynamic principles of information theory. Emergent gravity implies that gravity arises from the microscopic degrees of freedom of spacetime, similar to how temperature emerges from the collective behavior of molecules. This theory challenges the traditional view of gravity, but aligns with the thermodynamic properties of black holes. Verlinde's hypothesis draws on concepts from holography, proposing that gravity emerges from the entropic forces associated with information stored on holographic screens. This approach links gravity to the second law of thermodynamics, offering a novel perspective on its origin and nature. Despite these intriguing theories, the empirical evidence for gravity remains overwhelming. Gravity's existence is supported by a vast body of empirical evidence. Experiments such as the Cavendish experiment, which measured the gravitational constant, and observations of planetary motion provide irrefutable proof of gravity's effects. The Cavendish experiment, conducted in the late 18th century, measured the force of attraction between two masses, allowing for the calculation of the gravitational constant, g. This experiment confirmed Newton's law of universal gravitation with remarkable accuracy. Henry Cavendish used a torsion balance to measure the tiny force between lead spheres, providing the first precise value of g. This groundbreaking work demonstrated the universal nature of gravity and enabled accurate calculations of planetary masses and densities. Gravitational lensing, a phenomenon predicted by Einstein's general relativity, occurs when light from a distant object is bent by the gravity of an intervening massive object. This effect has been observed and documented in various astrophysical contexts. Gravitational lensing provides direct evidence of the curvature of spacetime. The bending of light around massive objects such as galaxies and black holes has been observed using telescopes, confirming the predictions of general relativity. Einstein's theory predicts that massive objects distort the fabric of spacetime, causing light to follow curved paths. Observations of gravitational lensing, such as the famous Einstein cross and the detection of lensing by galaxy clusters, provide compelling evidence for general relativity's validity. The Global Positioning System, or GPS, relies on precise time measurements from satellites. These measurements must account for the effects of both special and general relativity, demonstrating the practical applications of our understanding of gravity. GPS satellites orbit the Earth at high velocities and altitudes, experiencing both time dilation due to their speed, special relativity, and the weaker gravitational field, general relativity. Corrections based on these relativistic effects are essential for the accuracy of GPS technology. Without accounting for the time dilation effects predicted by Einstein's theories, GPS systems would accumulate errors of several kilometers per day. This practical application underscores the importance of relativistic corrections in modern technology. One common misconception is that gravity is a force similar to electromagnetism, or the strong nuclear force. In reality, general relativity describes gravity as the curvature of spacetime, not a force acting at a distance. General relativity replaces the Newtonian concept of a force with the idea that mass curves spacetime, and objects move along geodesics, the straightest possible paths in this curved space. This geometric interpretation of gravity has been confirmed through multiple experimental tests. Einstein's field equations describe how mass and energy influence the curvature of spacetime, dictating the motion of objects. This paradigm shift from force to geometry provides a deeper understanding of gravitational phenomena, from planetary orbits to the dynamics of the cosmos. Proponents of the flat Earth theory often dismiss gravity, suggesting alternative explanations for phenomena like the motion of celestial bodies and the behavior of objects on Earth. These claims lack scientific basis and ignore overwhelming evidence. The flat Earth theory fails to explain the observed curvature of the Earth, the consistency of gravitational acceleration, and the behavior of satellites in orbit. The theory also disregards the extensive body of evidence supporting the round Earth model and the laws of physics. Flat Earth proponents often rely on visual misinterpretations and anecdotal evidence, ignoring robust scientific data. The round Earth model, supported by observations from space, satellite imagery, and gravitational measurements, remains the cornerstone of modern geophysics and astronomy. Dark matter, an unseen form of matter that does not emit light, is inferred from its gravitational effects on visible matter. Its existence is essential for explaining the rotation curves of galaxies and the large-scale structure of the universe. Observations of galaxy rotation curves reveal that the outer regions of galaxies rotate faster than can be accounted for by visible matter alone. This discrepancy suggests the presence of dark matter, which exerts gravitational influence but does not interact with electromagnetic radiation. Dark matter constitutes approximately 27% of the universe's total mass energy content. Its gravitational effects are observed in galaxy clusters, gravitational lensing, and the cosmic microwave background, providing indirect evidence for its existence. Dark energy, a mysterious form of energy driving the accelerated expansion of the universe, poses additional challenges to our understanding of gravity. It accounts for approximately 70% of the total energy density of the universe. The discovery of the accelerating expansion of the universe based on observations of distant supernovae led to the hypothesis of dark energy. This phenomenon requires a modification of the cosmological constant in Einstein's equations, indicating that our understanding of gravity and the universe is still incomplete. Dark energy's repulsive force counteracts gravity, influencing the universe's large-scale dynamics. Understanding its nature and origin remains one of the most significant challenges in modern cosmology. Various theories, including quintessence and modifications to general relativity, have been proposed to explain dark energy, but its exact nature remains elusive. The detection of gravitational waves by the LIGO and Virgo observatories has opened a new window into the universe. These ripples in space-time, caused by massive accelerating objects like merging black holes, provide direct evidence of gravitational interactions. Gravitational waves were first predicted by Einstein's general relativity. Their detection in 2015 confirmed this prediction and allowed scientists to observe events such as black hole mergers, providing new insights into the behavior of gravity in extreme conditions. Gravitational waves carry information about their cataclysmic sources, such as neutron star collisions and supernovae. The study of these waves helps scientists test general relativity under unprecedented conditions and explore the properties of black holes and neutron stars. Black holes, regions of space-time where gravity is so intense that not even light can escape, challenge our understanding of physics. The study of event horizons and Hawking radiation offers insights into the interplay between gravity, quantum mechanics, and thermodynamics. The event horizon of a black hole marks the boundary beyond which nothing can escape. Hawking radiation predicted by Stephen Hawking suggests that black holes can emit radiation due to quantum effects near the event horizon, leading to the gradual evaporation of black holes over time. Hawking's theoretical work combines principles of quantum mechanics and general relativity, proposing that particle-antiparticle pairs near the event horizon can result in radiation escaping from the black hole. This process implies that black holes are not entirely black but radiate energy, challenging our understanding of entropy and information loss. Gravity plays a crucial role in aerospace engineering, influencing the design and operation of aircraft, rockets, and satellites. Understanding gravitational forces is essential for calculating trajectories, orbits, and fuel requirements. The principles of gravity are applied in the design of spacecraft trajectories, including gravitational assists or slingshot maneuvers, which use the gravity of planets to accelerate and redirect spacecraft. These techniques allow for more efficient missions, saving fuel and extending the reach of space exploration. Gravity also affects the design and construction of buildings, bridges, and other structures. Engineers must account for gravitational loads to ensure stability and safety. Structural engineers design buildings and bridges to withstand gravitational forces, considering factors such as weight distribution, material strength, and load-bearing capacity. This ensures that structures remain stable and safe under various conditions, including earthquakes and strong winds. The quest for a theory of quantum gravity aims to unify general relativity with quantum mechanics. This theory seeks to describe gravity at the smallest scales, resolving conflicts between the two frameworks. Efforts to develop a theory of quantum gravity include string theory, which posits that particles are one-dimensional strings, and loop quantum gravity, which suggests that space-time itself has a discrete structure. These theories aim to reconcile the apparent incompatibilities between general relativity and quantum mechanics. Quantum gravity research explores phenomena such as black hole singularities in the early universe, providing insights into the fundamental nature of space-time and the origins of the cosmos. Advancements in our understanding of gravity will continue to impact space exploration. Accurate gravitational models are essential for planning missions to other planets, moons, and beyond. Future space missions, including those to Mars and potentially interstellar travel, rely on precise gravitational calculations for navigation and landing. Improved understanding of gravitational interactions will enhance mission success and safety. Innovations in propulsion technology, such as ion drives and potential warp drives, also depend on a deep understanding of gravity in space-time. These advancements could enable faster and more efficient travel through space, expanding humanity's reach into the cosmos. Gravity is a fundamental concept in science education. From elementary school through advanced physics courses, understanding gravity provides a foundation for learning about other forces and phenomena in the universe. Educators use a variety of methods to teach gravity, including experiments, simulations, and demonstrations. Simple experiments, such as dropping objects of different masses, illustrate the uniform acceleration due to gravity, while advanced simulations model planetary orbits and gravitational interactions. Promoting a clear understanding of gravity among the public helps combat misconceptions and pseudoscientific claims. Public outreach and science communication play vital roles in educating people about the true nature of gravity. Public science initiatives, such as documentaries, lectures, and interactive exhibits, engage audiences and explain complex concepts in accessible ways. By addressing common misconceptions and providing accurate information, these efforts foster a scientifically literate society. Gravity's role in shaping the universe prompts philosophical questions about the nature of reality and our place within it. The study of gravity intersects with metaphysical inquiries about existence and the fabric of the cosmos. Philosophers and scientists alike ponder the implications of gravitational theories for our understanding of reality. General relativity's depiction of curved space-time challenges traditional notions of space and time, while quantum gravity theories raise questions about the fundamental structure of existence. Exploring gravity also highlights the limits of human knowledge and the ongoing quest for understanding. Despite significant advancements, many aspects of gravity remain mysterious, underscoring the importance of continued inquiry and exploration. In conclusion, the notion that gravity doesn't exist is not supported by scientific evidence. From the precise measurements of gravitational constants to the observations of gravitational lensing, and the practical applications of relativity and GPS technology, gravity remains a cornerstone of modern physics. While alternative theories and challenges to our understanding of gravity continue to emerge, they do not negate the existence of gravity, but rather enhance our comprehension of this fundamental force. If you enjoyed the video, please like so we can get this video to as many people as possible out there. Subscribe, hit that bell notification for alerts on all our new videos, share and comment below on topics you want us to cover on the channel. Thanks for watching and see you on the next one.